Welcome back to Robbie's Office Hours. Today we're talking about complex roots, which are solutions to the characteristic equation of a second order constant coefficient linear homogeneous differential equation, okay? These things get a little crazy in terms of all of their descriptive characteristics for them, right? It's a second order constant coefficient, it's linear, and it's equal to 0, so it's homogeneous. Okay, now these are complex roots, which means that they're complicated, which is not true. Okay, complex is a complex number. All right, it's just not a real number. It's a complex number. It looks like a plus bi or something along those lines, where I is the imaginary unit. Okay, so find the general solution to this. Again, the methodology is exactly the same for all of these. We find the characteristic equation. Characteristic equation is found by substituting in y equals e to the rt. That ends up giving me the quadratic r squared plus 2r plus 10 is equal to 0. Okay? So now I need to find the roots. And you stare at this for a little while and you're like, well, I'm going to try and factor it. And you're like, okay, I need two numbers that multiply to give me 10. So that's 10 and 1, 5 and 2, or any number of fractions and all that kind of craziness. But whose sum is equal to 2. And that doesn't, like 10 and 1, not great. Like negative 10, negative 1, not good. 2 and 5, like not great. Okay, you quickly realize that factoring's probably not the right move. So let's just complete the square. How does that look? Well, I'm going to look like r squared plus 2r plus 1. And then I'm going to have to add a 9 in on that. So I get a 1 plus 9 gives me my 10. Okay? Now I notice this part is a perfect square. That thing looks like r plus 1 squared plus 9 is 0. Okay? So then I move the 9 over. I end up getting r plus 1 squared equals minus 9. Okay? What are the roots of that? The roots of that are 3i and minus 3i, okay, where I is the imaginary unit, so imaginary squared is minus 1, okay? So this is telling me r plus 1 is going to be plus or minus 3i, which tells me that r is equal to minus 1 plus or minus 3i, okay? So those are my roots. Now notice that they are distinct, okay, and they are complex conjugates of one another, meaning that one is like a negative 1 plus something, the other one's negative 1 minus that same something. Okay? So those are my roots. But at the end of the day, it doesn't matter what these things are. Like, I just care about what are their coefficients. So this like negative 1 here and the 3 here. Okay? So what are my solutions going to be? The solutions... Now remember, if this next part is a bit of a shock, you're like, wait a second, where did that come from? Go check out the video where I actually derived that the roots are what they are. Okay, it comes from Euler's identity and all that stuff. So what do I end up getting? Corresponding to the negative 1, I'm going to get an e to the negative t. Corresponding to the 3, I'm going to get a sine and cosine of 3t. So one of my solutions will be e to the negative t cosine of 3t, and the other solution will be e to the minus t sine of 3t. Okay, those are my two solutions. Again, go check out the video on complex roots and how I derive this, and you'll see that that's what you get. Now, check out the other video on the Wronskian, which tells you that these two solutions are actually linearly independent. And if they're linearly independent, then we know what the y homogeneous solution is. That's equal to constant times one of them, e to the minus t cosine of 3t, plus constant e to the minus t sine of 3t. And there you have it. There's your homogeneous general solution to your, wait for it, second order constant coefficient linear homogeneous differential equation. Okay? So hopefully that helps. Again, the methodology is the same for all of these. And as always, like, subscribe, share with your friends, comment down below. We'll keep on moving.